In the last section, we started to look at antiderivatives and indefinite integrals, and we really tried to work backwards from what we already knew about derivatives. And something else I know about derivatives is that beyond the power rule and some basic derivatives like e to the x and natural log of x, we needed other derivative rules like the quotient rule, the product rule, the chain rule. So it turns out that integration also has some specialized rules. There are no, unfortunately, there's no one-to-one correlation. There's no quotient rule for integration or a product rule. But integration by substitution is the closest that we can come to kind of a chain rule or a reverse chain rule for integration. So here we're going to just remember the chain rule. We're going to look at integration by substitution, which hopefully should be a way to undo this chain rule. So here, just to refresh our memories, I have a function y equals 1/6 times x squared plus 2x plus 5 to the 6th power plus 7. We'll find y prime, and this is, in fact, a chain rule. So you may want to, somewhere off to the side, I honestly, I don't remember what variable we were using now off the top of my head. I'm going to use u. I think that's what we were using. U would be this inside part right here, this x squared plus 2x plus 5, and u prime, that is 2x plus 2. So when I rewrite this equation in terms of u, this is y equals 1/6 times u to the 6th plus 7. And then we say, okay, we can take the derivative of this using our chain rule. This is going to be y prime. 6 and 1/6, those are going to cancel each other out. So I have u to the 5th power times u prime. And then the derivative of 7, well, that's just 0. So when I take my u and u prime, plug those back in, I'll have x squared plus 2x plus 5 raised to the 5th power times u prime, 2x plus 2. So here's my derivative. This is my y prime. And what I want to see is if we can take this process and go backwards from it. We're going to do that using this method of integration by substitution. So actually in the next problem, I'm going to integrate exactly what I ended up with, and my hope is that I end up with the same function that we began the first example with. So let's walk through the steps of integration by substitution. Just like we did with the chain rule, you're going to start by choosing a quote inside function, and we'll use u equals g of x. Sometimes this is even called u substitution. So you're going to pick an inside function. So if I'm looking at this next integral, your inside function here might be a little bit more difficult to pick out. Here it might be a little bit more difficult to pick out because you have x squared plus 2x plus 5 to the 5th power, and you have this 2x plus 2, both of which are inside parentheses. Parentheses, remember, those were something that helped us make our decision about what u should be when we were doing the chain rule. But generally, if you're stuck between two choices, I always go, you can think about it two ways. You can think about it as the factor or the part of it that has the highest power of x, or generally just the most complicated part of your function. So usually that's just the term with the higher, the factor with the highest power. So I'm going to pick u equal to x squared plus 2x plus 5. And the whole goal of integration by substitution is we have this difficult looking integral that yeah, we could FOIL that out 5 times and then multiply that by 2x plus 2, but who wants to do that? It's a fairly difficult looking integral. The whole point of this process is to take this difficult looking integral and make it easier to deal with. So we're going to try and rewrite this integral in terms of u. That's the substitution that's happening. So we've chosen our inside function. Next, we need to find the differential du. Because at the end of this, I'm going to have something u to something. I want to integrate in terms of u, and I can't leave this dx stuff here, so I need u instead. So du is simply just the derivative of u, which in this case is 2x plus 2 times dx. So we just need to multiply that by dx. That's really the only extra added thing when we're looking for this differential du. In step 3, it says you may need to, quote, solve for other parts of your integrand, so other things that are inside of your integral. And we'll look at some examples where we need to do that. Here we should see, hey, x squared plus 2x plus 5, that is my u, and 2x plus 2 dx, that is my du. So this one works out really nicely. There's no extra algebra that I need to do. So, okay. Step 4, we want to rewrite this integrand in terms entirely of u and du. We don't want anything in terms of our original variable, so we shouldn't have any x's left over. So I'm going to take out, u was x squared plus 2x plus 5. I'm going to take out x squared plus 2x plus 5. I really have u to the 5th power, so that was this piece right here. And then du is 2x plus 2. That's this piece right here. So I'm just going to take out 2x plus 2 and replace it with du. This integral is a whole lot easier to manage. It's a whole lot easier looking than the one that we started with. And that is your goal with this integration by substitution. You want to take this difficult looking integral and break it down into something that's a little bit easier to manage. So, okay, we've rewritten our integral. Step 5 then, evaluate this new integral. So now we need to go and find our antiderivative. So here, this is just a power rule. This will be u to the 6th divided by 6, plus, of course, my constant of integration c. Can't forget about that. And then step 6, I want to rewrite in terms of your original variable. So I just want to rewrite this. The way I think about it is if I started with something in terms of x, I would like to end with something in terms of x as well. So here, u to the 6th, that's x squared plus 2x plus 5 to the 6th power divided by 6 plus my constant of integration c. Here is my solution. So I should be able to check at this point, hey, is this what we started with? And yeah, for the most part, it is. A couple things that are a little bit different. Here, this 1/6, we just wrote that a little bit differently. Here, you could pull this division by 6. You could rewrite that as 1/6 times x squared plus 2x plus 5 to the 6th power. So that's not a big deal. The one thing that does get lost in this translation, though, is that constant at the end, plus 7. There's really no way for us to know what that constant should be if we're just starting with the integral. Of course, if we had a point on our graph, we could do a little bit of substitution at the end of our problem to find out what that is, but without knowing that point on our graph, we can't find out what our constant of integration c is. So this is the general process of integration by substitution. You're choosing an inside function u, just like we did with the chain rule. You'll find your du. You'll make your substitutions. So you'll substitute in for your original integral. You will integrate that simplified integral. And then once you're all done, once you've integrated, then we can go ahead and substitute back in our original variable. Every single one of the problems that we look at today is going to follow this same pattern. So, all right, let's look at another example here. I have the integral of 3 times the quantity 3x plus 4 raised to the 6th power dx here. So here, let parentheses help you just like they did with the chain rule. Usually those are a pretty big hint as to what your u should be. I'm going to choose this piece right here to be my u. So u is equal to 3x plus 4. I need to also find du. As soon as you identify what your u is, you should go ahead and find du right away, immediately after that. Du I know is just the derivative of u, so that's the derivative of 3x plus 4, which is 3 times dx. I just need to multiply by dx here. And then I'll say du, hey, I can kind of stretch around here. This is all multiplication. So if you needed to, you could rewrite this as 3x plus 4 to the 6th power times 3 dx. And then I think it becomes much more clear. I'd say, okay, this is my du, here is my u, and I'm ready to make my substitution. But you don't have to necessarily rewrite that. You can, since this is all multiplication, you can kind of stretch around and you could say, okay, here is 3, here's my dx, this is my du, and actually let's maybe highlight, here is my du, that's this piece right here, and then the 3x plus 4, that is my u. So once you've identified your u and your du, it doesn't look like I have any other solving to do here. It's a relatively nice substitution. I'm going to go ahead and make my substitution now. So this is really the indefinite integral of u. Remember, here we had that 6th power here, u to the 6th power du. So here I have my indefinite integral. This is a lot simpler than what we started with. So we're going to go ahead and evaluate this. Add 1 to the power, u to the 7th, divided by my new power of 7, plus my constant of integration c. And then the last thing I need to do, I just need to take my 3x plus 4 and plug that back in for u. So here I'll have 3x plus 4 to the 7th power divided by 7 plus my constant of integration c. So these are relatively nice substitution problems. We really didn't have to do any extra solving here in step 3. In the next video, we'll look at some examples that are still integration by substitution, but we're going to see what this means. What does it mean if we have to solve for other parts of our integrand here? So we'll take a look at that in the next video.